Greetings and salutations. This is Calculus with Dr. Katz. Today, I want to do an example of implicit differentiation. This is the technique that you use when you want to take the derivative of a curve that isn't necessarily a function. As you know, in order for a curve to be considered a function, it has to pass the vertical line test. But not all curves do this. You can draw any curve on the plane. And although this curve doesn't pass the vertical line test, meaning it's not a function, you can still pick points on the curve and you can still draw tangent lines to those points. And those tangent lines still have slopes, and so the curve still has derivatives. But how do we take a derivative of something that's not a function? For example, let's look at the curve given by the equation 2x cubed plus y cubed is equal to 5xy. What this curve looks like when graphed is something like this, and it's known as a folium. And you can see that this is not a function. It doesn't pass the vertical line test. This equation, then, we say, is given implicitly. And it's not a function. It's not like y equals something. It's got x's and y's, and they're all mixed in together. That's why we say that it is an implicit equation. And let's say that we want the equation of the line tangent to the curve at the point 1, 2. Now the first thing that we have to check is that the point 1, 2 is actually one of the points that makes up this curve. So we just plug in x equals 1 and y equals 2, and you get 2 plus 8 equals 10. And yeah. So what do we need? Well, in order to find the equation of a line, we need a point. And we have that. It's right here. And we also need a slope. Now, when we say slope, we normally think rise over run, or maybe delta y over delta x. But we're in calculus now. And so we really want to think of this as dy over dx. So in order to get dy dx, we need to differentiate both sides with respect to x. Differentiate both sides with respect to x. Meaning, perform d dx of the left-hand side plus, equals d dx of the right-hand side. So now let's begin our differentiation process. We know from the power rule that the derivative of 2x cubed is 6x squared plus, but now look, we're taking derivative of with respect to x, but now our variable is y, so how do we take the derivative of y cubed? Well, this is where the implicit differentiation comes in. So let's just work over here for a second and tackle differentiating y cubed. Let's just say that u is y cubed. And the trick is think of y like a function. So we say that y is some sort of function. And now, by the chain rule, we know that du dx is equal to du dy times dy dx. Du dy is easy. It's just 3y squared. And dy dx, we don't know. We don't know what this function is, so we just leave it as dy dx. And so the derivative of y cubed with respect to x is 3y squared dy dx. We do the same thing to the right-hand side, but here we need an application of the product rule. This is 5x times y, so you do the derivative of the first times the second plus the first times the derivative of the second, and the derivative of y is dy dx, because again, we're thinking of y like a function. So there's dy dx. That's what we're looking for. So now solve for dy dx. And so let's do that. We bring all the terms with dy dx over to one side, and all the other terms to the other side, and factor out dy dx. And divide. And so now we have a formula for the derivative at a point on the curve that was given before. Remember, the curve that looks like this. Something like that. So we have a formula for the derivative of this curve. And we wanted the derivative at the point 1, 2. So we want dy dx at the point 1, 2. And let's see, if y is 2, there's 10 minus 6 divided by, well, 3 times 4 is 12 minus 5. And so the derivative at this point was 4/7. So now we just use point-slope form. And we say that y minus 2 is equal to 4/7 times x minus 1. Or if you solve for y, let's see, y minus 2 is equal to 4/7 x minus 4/7. And that means that y is equal to 4/7 x. So you're adding 2, and 2 is 14/7, so plus 10/7. And this is the equation of the tangent line that we were looking for. If you have any questions, or you just found the video helpful, please leave a comment below. But for now, I'm Dr. Katz, and have a great day.